Welcome to Mechanical Vibration and Measurement Lab. My name is Hamid, and I'm going to show you an interesting experimental testing in mechanical vibration, which is to visualize which is to collect different types of vibration response of a single degree of freedom system. So basically what we do have today is we have already instrumented a speaker here with different types of transducers to measure displacement, velocity, and acceleration response. So I'm going to start with measuring and collecting displacement response. To collect displacement response, we are using actually a laser displacement sensor or a laser triangulation displacement transducer, which is basically this little black box here. So this transducer works on the principle of triangulation and using the reflected beams. So the transducer actually requires a kind of power supply, which that power supply is provided by this box here. So it provides DC voltage and then also the output of the displacement sensor, which is actually also voltage, goes into this box again, and we can collect the voltage of the displacement sensor using this BNC cable. And the BNC cable, the output of the BNC cable goes into the oscilloscope, and then we can visualize the displacement response of the signal of the system. So the next type of transducer which we've got here is LDV. Basically this transducer here, which is laser Doppler vibrometer, which works on the principle of Doppler shift, and the output of displacement of the vibrometer LDV is also voltage, which directly goes into our oscilloscope here. The point is that we have tried our best to set up the experimental setup in a way that the laser beam of LDV focuses on the same point as the the displacement sensor. So both they are all vibrate. They are collecting the response of almost the single point. So the next type of transducer which we've got here is accelerometer to measure acceleration response. So you know that for measuring acceleration there are different types of accelerometer. But what we are using here is the type of IEPE or integrated electronics piezoelectric, which these types of accelerometers are based on the piezoelectricity, and because they have piezoelectric material inside, and those types of materials, the ones that are under vibration or deflection, they produce charge. And so we need to have a kind of conditioner or converter to convert charge into voltage. So these types of IEP accelerometers, they have an embedded circuit which converts generated charge into voltage. And so we can collect the voltage using oscilloscope or different types of acquisition system. So these types of IEP accelerometers, they do also need a kind of current supply, a constant current supply, which here we provide the current supply by this signal conditioner. So the signal conditioner here provides the current supply. And then also the output of accelerometer goes into the signal conditioner here. Because signal conditioner here is also a kind of filtering, we can filter noise, and also we can increase signal to noise ratio as well. And the output of signal conditioner here, its output will go into the oscilloscope to collect the signal. So this oscilloscope here, it does have 4 channels, 1, 2, 3, and 4. So we connect channel 1 to the output of signal generator. So this output is for signal generator. And then we are using a splitter here. One branch goes to speaker, and another branch goes to channel 1 to visualize the generated sinusoidal signal. Channel 2 goes to displacement sensor. Channel 3 goes to LDV, and channel 4 goes to accelerometer. So I'm gonna just turn on the signal generator, and then we can visualize it. So channel 1, which you can see the yellow trace, is for acceleration signal. channel 2 is for displacement, channel 3 is for velocity, and channel 4 is for acceleration signal. Then what we can do, we can increase the excitation frequency to see how it goes. And another important point that I need to mention here is just what we collect here is just voltage. But if you want to know the exact value of acceleration, velocity, or displacement, then you need to multiply the collected voltage by calibration factor for each individual transducer. So now, if we increase the frequency from 10 Hertz to 20 Hertz to 30 Hertz, then you are collecting different values and different frequencies for for the vibration response. But the interesting thing is that the displacement, velocity, and acceleration responses, as I'm sure you all know, that there are a relationship between them. So meaning that you can simply plot the acceleration response obtained by displacement response and acceleration response obtained by velocity response, because you know that the velocity is the first derivative of displacement response, the acceleration is the first derivative of velocity response, or is the second derivative of displacement response. So you can, by changing the frequency as well, you can also plot the frequency response function and see how you can get closer to what's going to happen when you get closer to natural frequency of the system because when you increase the frequency, your response increases, and then it increases up to a certain value, which that certain value shows you the fundamental frequency, natural frequency of your system, which basically for this system, because we assume that the system has only single degree of freedom system, it does only have a single natural frequency. And so we are going to publish the data sets for different frequencies, and then we are also provide you with the calibration factors, so you can easily just dig out you can go through the details of the signals. You can work it out, the relationship between the signals, and also you know that there is a phase shift between the displacement signal and velocity response, and also the acceleration response. So you can simply just understand those interesting and of course important concepts. Just another view of experimental testing. So basically this is this box here is displacement sensor, and you can see we've got actually an accelerometer attached on top of the cone of the speaker, and you can see a red light over there. That red light is the beam of LDV, and this is our LDV here, which is pointing to the top of the cone of the accelerometer. And also this is, as I already mentioned, this is signal conditioner connected to the accelerometer, and this is the power supply for triangulation displacement sensor, and this is the switch. This is the switch for turn on and turn off the displacement triangulation displacement sensor. Okay, this signal is a close-up of the vibration response for different transducer for 10 Hertz. As you can see here, it's just 10 Hertz. I have now increased the excitation frequency to 20 Hertz to let you know that the yellow one is the excitation signal, green one is displacement, blue one is velocity, and red one is acceleration. As you can see here, we are getting reasonable and pronounced signal for all three transducers. So we can increase the excitation frequency to above 20 Hertz now. I just do that. So I increase it to, this is 40 Hertz, and you see that the at least you can see clearly for the green signal that the amplitude of vibration decreases. The amplitude of actually displacement signal decreases by increasing the excitation frequency. So it depends on the natural frequency, and it depends on frequency response function of the system for a single degree of freedom system, which I leave it to you to dig it out further once we actually we share the data sets. So I just increase more. You see that the acceleration signal increases, so I need to increase the scale of acceleration signal. I increase just each block is now 100 millivolt. If I increase the excitation frequency further, now it's the excitation frequency is 100 Hertz, and you see that the amplitude of the actual displacement also is decreasing. So by doing this, by collecting peak-to-peak of displacement, velocity, and acceleration signals, we are able to plot the frequency response function for different types of vibration response. I think that's about it for today. Hopefully it's a kind of concise and interesting video. Thank you very much.